Okay, thanks a lot. So again, I wish to thank the organizers for inviting me to give this talk, and it's based primarily on a work that we did in 2016, and that's what I'm going to be talking about. And this will relate to high redshift H1, so just one thing of many things we have tried, and the nature of dark matter, and I'll focus primarily on ULA as the dark matter. So here is a view graph, and I think this view graph is nice in the sense that it summarizes the role of dark matter in cosmology in more ways than one. This is actually a snapshot of density perturbations at redshift of 1000. 1000 is important, that's when recombination happened. And of the multiple component fluid in the universe, like it actually shows you what different components are and how do they behave. So it has what is called cold dark matter. This is the usual cold dark matter. So we have, this is not an alternative model. The usual cold dark matter. There are baryons, there are photons, and there are massive neutrinos. And you can see they all behave differently. I mean, and their physics we know. CDM basically is a completely featureless evolution. You can see there is only one scale in the problem, which I will show in the next view graph. Baryons and photons, they oscillate together as a coupled fluid. And massive neutrinos, once they enter the horizon, they just free stream. I mean, I put like very light massive neutrinos here. And you can see it's actually remarkable that like around 30 years ago, any of these possibilities could be dark matter, what we call dark matter in the universe. I mean, dark matter could be massive neutrinos. This was proposed in 70s and 80s and ruled out in late 1980s only. Baryons or baryonic kind of particles, charged particles, were proposed as dark matter candidates by many particle physicists, but they have also been ruled out. CDM remains the featureless thing that we see out there. This seems like the only viable model of the dominant component of the dark matter, that it is actually very cold. So if that is a model we have, it's good to review the scales in the problem. What are the different scales in the problem? And we are going to introduce more scales as we go on. And one is a matter radiation equality, and this completely determines the shape of CDM perturbations. If you just focus on CDM perturbation, matter radiation equality scale suffices. Then the next scale is the sound velocity of the baryon photon fluid. It's much larger actually. And I'll not discuss this much in this talk, but if you had a baryonic component of dark matter, then this will become important. It will be the sound velocity in that component. Then, of course, there is silk damping, and silk damping, of course, plays an important role in determining the shape of CMB anisotropies that we have all seen, that they rise high and then they taper off for large values of L, and that is largely owing to silk damping. And then, of course, the final scale in the problem is the free streaming of massive neutrinos. If you have massive neutrinos or massless neutrinos for that matter, they free stream until the horizon. And that gives you a typical scale in the problem. And that scale is generally extremely large. I mean, that could be hundreds of megaparsec. And that is how we know that this is not the dominant component of dark matter in the universe, because we see matter at much, much smaller scales. So here is SDSS result. It's a plot. It just shows you the kind of power spectrum that has been detected from galaxy clustering. And one look at it and we know that this looks much more like CDM than anything else. Of course, it has imprints of the baryonic perturbations on it, which I'm not trying to show here, and which is called baryon acoustic oscillations. But they are very tiny. I mean, you have to actually see it carefully. But it looks very featureless. But one important thing about this plot is the scales that have been shown here. So this largest scale shown here is, of course, like around 0.04 or something on the left side of the figure. And it is the smallest scale, which corresponds to K of around 0.2. That is important for us. Roughly this scale, or maybe K equal to 0.1, it's a matter of opinion actually, K equal to 0.1 or K equal to 0.2. These is the scale where density perturbations become nonlinear at the present. And beyond this scale, we cannot connect this kind of data to theory based on perturbation theory. I mean, in the early universe, and that's what we actually try to do. We want to compute things using linear perturbation theory and compare it to data. But that is only possible if we have scales like K equal to 0.1 or 0.2 maximum. Beyond those scales, this data actually extends to larger scales, but it has not been shown here because the aim of this figure also is to underline the importance of linear perturbation theory. So that number needs to be kept in mind, that From all the observations we have done so far of galaxy clustering, the smallest scale that we can probe currently is around k equal to 0.1, make it k equal to 0.15. It is actually amazing that one may ask, what is the smallest scale that can be probed by CMB anisotropies, Planck? And that scale is comparable. That's around 0.152 actually. So the lesson is that current observation, the best observation we have currently, they allow us to probe very large scales, surely. I mean, CMB allows you to probe k equal to 10 power minus 3, which of course is not shown here because this is galaxy power spectrum. But the smallest scale that we can probe with any level of confidence using the best observations we have so far is around 0.15 or 0.1. So here is, based on Planck results, here is a summary of what has been found. And I think I'll not dwell upon primordial perturbation because people have already discussed it. Again, Planck data gives you, like the baryonic component, it determines it extremely well. We can focus on non-relativistic component of the dark matter. Notice again that this again is computed extremely well. I mean, this is one of the best observation you can think of. Like, I mean, but one needs to keep in mind that all of it is based on data up to k equal to 0.1 and not beyond that. Hubble's constant, again, that's another story. That is a very precise measurement of Hubble constant. Massive neutrino, again, there are upper bounds on massive neutrino from the data, but this has not just come from CMB, but other data sets have also been used. And we are still far away from the minimal that particle physics give us based on the hierarchy data, but one will get there. Again, massless neutrinos, number of degrees of freedom are fixed, total matter content, spatially flat universe. But what is more important for us here is the non-relativistic component of dark matter. The lesson here is you cannot play around with theory of dark matter if you are dealing with scales which are small, larger than around 0.1, because that will violate this observation. But you can play around with it if you're dealing with scales smaller than that. And we also have problem with CDM at sub-galactic scales. Like, I mean, this has been reported for the past 20 years or so. I mean, 3 sets of problems are generally reported. There is a missing subhalo of galaxy, the Milky Way. The simulation, this is mostly based on simulations. They produce a lot of substructures. And it's 25, there are 25 times more dwarf spheroids than detected in Milky Way. So there is clearly an indication there could be less power at small scales as compared to what the usual CDM model predicts. There is Cuspy profile. I mean, again, simulations suggest Cuspy profiles, but observations suggest it's flat. It could be owing to interacting dark matter. It could be just going to baryonic features. I mean, the point is it may have nothing to do really with dark matter. Then other set of simulations suggest that substructures of Milky Way are way too big. I mean, the point, one of the ways to explain away missing subhalos of Milky Way was that the halos, dark matter halos, are really tiny. And so once baryon starts falling in it, like even one like supernova explosion can destroy them. So that's why we don't see them. There are all these dark matter halos out there, but they have not captured baryons, because when they captured baryons, they easily were destroyed, the baryonic halos. But too big to fail, say no, not really. Actually, the simulation suggests that substructures of Milky Way are quite big. They should not have been destroyed by those kind of processes. So this is called too big to fail conundrum. Well, these three, again, are based on nonlinear physics. Like, again, one should say that all of these would invoke scales which are far smaller than the scales at which CMB observations or galaxy clustering observations can be compared to linear theory. So that is one of the reasons why it is very difficult to either verify it or rule it out beyond a point. Again, one of the things that I think we are having this meeting because of this, that for a very long time after 1990s, it was believed that the dark matter is WIMP. It is the lightest supersymmetric particles or a variant of that. And that's what people searched for a very, very long time. And if you look at the kind of cross sections people have reached, I mean, look at the right panel. I mean, they have reached level of cross section like 10 to minus 45. I mean, this is orders of magnitude smaller than weak interaction cross sections. And that's what people have reached, and they have found nothing. So these limits have improved by orders of magnitude in the last 10 years alone. And people thought they will find something in this parameter space, like this mass range of WIMP, like 10, between 100 to 1000 giga electron volt, or and kind of cross sections smaller than 10 power minus 42, but certainly larger than 10 power minus 45. But nothing has been found so far. So that's why the excitement about another dark matter candidate. So it is partly motivated by the failure of the experiments to detect the dark matter, the WIMP dark matter, that is. So there are a whole range of alternative dark matters, and I'm going to talk about just one. But well, the point is, an alternative always there are many, while the standard there is only one. So there could be warm dark matter. Again, all of these models are motivated by the fact that we believe that there is lack of power at small scales as compared to the CDM model. So that is the motivation for all of these models. So warm dark matter, of course, would say, okay, it's not really cold and small scales, so it can actually deplete power at small scales. Late forming dark matter, their dark matter may not even be there and it formed at a late stage, and this will also cut power. And I'll discuss mostly ultralight axion, and this is another class of dark matter, which in fact is just a scalar field, and it can act like a dark matter, and it can also diminish density perturbations at small scales. Then you can have decaying dark matter particle. The list goes on, and I'll just focus on ultralight axions. So again, for ultralight axions, and much has been said about this in this meeting on ultralight axions. So just one view graph to summarize how it actually works. It's remarkable. This is a classical scalar field, and it behaves like a cosmological constant at early times. And when the mass of the particle is much smaller than the expansion rate, but at late times, when the mass becomes larger than the expansion rate, or expansion rate becomes mass is invariant, expansion rate is decreasing. The background, it oscillates, and on average, it behaves like matter. So it can mimic normal matter, like 1 by a cube at late times. So the background evolutions does suggest that we should look at the perturbation component of this theory. And the perturbation is very interesting, that it has an effective sound speed, this scalar field. And this effective sound speed is not zero as it should be, as it is for the normal CDM component, but finite, and it changes with time, and it's a function of scale. At very early time, CS score goes to 1, which will suggest that nothing can actually cluster below the horizon scale, but scalar field has little impact at that time. On gravitational potential, it doesn't matter. You can change things at very early times with little impact on observables at late times. At late times is when excitement comes, and when the scalar field energy density becomes comparable to radiation, because this density is falling as 1 over a cubes matter. Then if you had a normal CDM particle, the density contrast would have increased either as logarithmic of A when the scale enters the horizon in radiation dominated era, or as A if the scale had entered the horizon in the matter dominated era. But for a scalar field, that's really not true, because you can actually see that there is a finite sound speed which will prevent growth of perturbations below a certain scale for a certain range of times. And that's interesting, that this kind of, in a very natural way, this allows us to have models at which there is less power at small scales. At very late times, of course, CS goes to 0 and the scalar field behaves like pressureless CDM. Here is a plot which shows different power spectra against the usual lambda CDM model. And you can actually see that but they are tuned in such a way that you do not want them to differ from this up to k equal to 0.1. You can see that that's what I said. Up to 0.1 or 0.2, they should not differ much from the usual model. They should look more or less the same. But at smaller scales, there could be significant deviation. And you can see there are all range of model. LFDM is a late forming dark matter model. There is a charge decay model, which can actually have power even more than CDM, for reasons I'll not go into. You can have warm dark matter particle, which again will lead to depletion of power at small scales. And then there is ultralight axion model. Just one model is shown here, 10 power minus 24 electron volt. And yet again, you see that it leads to depletion of power at small scale. It'll be some exercise in coming years to actually be able to distinguish between these models. But for the time being, what we have is that a class of models which will lead to less power at small scales, and we want to know what could be observational consequences of this. So here is a list of the kind of cosmological observables we may have at small scales. And none of these observables, it must be admitted right away that none of these are at the same level as CMB, right? I mean, because there are modeling uncertainty. So a very powerful probe is Lyman alpha clustering, and I'm doing some work on it, but like it will take very far from where I want to be discuss it. But Lyman alpha is basically like this is not nonlinear. These are clouds which are formed between. We have detected them very well between redshift 2 to 5 now, and these are mildly nonlinear features of the density field, or so we believe, and we model it like that. But they can actually take you all the way to k equal to around 4 megaparsec inverse, which is the gene scale in the medium at like around 10 power 4 Kelvin. So it's a very powerful probe, and one people believe is going to lead to many discoveries of things at small scales. Epoch of reionization is another very active area of research. I work on that. And again, epoch of reionization is something that happens between a redshift of roughly 20 to 10, make it 8. But here again, if you have a dark matter candidate which has less power at small scales, halo population will decrease for the alternative dark matter. And the reionization history is different, and so is this fluctuating component, and that could potentially become a probe of the dark matter model. Something I'm going to discuss in some detail later on is collapse fraction of matter at high redshift. Now, this is something which is interesting, which was used as a probe of many models, like in late 1990s, before CMB results came, and this was not used a lot. But again, I will go into detail of how we use this information from initial density field to compute the collapse fraction at any redshift. And that in some cases can be compared to data. In particular, the H1 mass and the collapse fraction of H1 is known to us. And again, this is sensitive to K of the order of 0.5 megaparsec inverse. Finally, UCMB spectral distortion is a very powerful probe of alternative dark matter, but again, I'll not discuss this in this talk. My focus will be the middle two in this talk. So here, again, very briefly, I'll try to say how collapse fraction can be a probe of power spectrum. It's a strikingly simple idea, actually. The initial density field is Gaussian. So what we do is we take the density field in the universe and we filter it on a certain mass scale or length scale. And because it's a linear process, the density field is still Gaussian. And we ask the question, what fraction of this density field is a Gaussian, and the Gaussian becomes broader and broader as the time evolves. And at any redshift, we can ask the question, what fraction of it would have an overdensity more than the overdensity required for a virialized halo? That means that's what we mean collapsed. When something collapses, it virializes, and density contrast corresponding to that in the linear theory is 1.7. And actual density contrast is around 200. So we can actually ask this question. What fraction of this will collapse based on just the initial condition? We do not know what happens later, but we know the initial condition extremely well. So collapse fraction can simply be computed as an integral over this probability distribution from a value of density which we believe corresponds to the collapse density at a later time. And again, the important point here is that the power spectrum information comes in an exponent here. And that is a very, very important thing. Something that comes in an exponent suggests it's extremely sensitive probe. And by the way, this was a probe that was used initially to compute values of sigma 8 from cluster abundances. It's exactly the same approach. I mean, and it's a variant of what is called pressure sector formulation. If you take the derivative of the collapse fraction as a function of m, you'll get pressure sector mass function. So this is a probe was used in early days, and these days we rely much more for normalization of power spectrum on CMB data. But in early days, we actually depended on cluster abundances, and it is based on exactly the same approach. So collapse fraction is an extremely sensitive probe of matter power spectrum because the collapse fraction comes in the exponent. So if that exponent, that term is smaller than unity, then it is not a powerful probe. But if it is larger than unity, it is an extremely powerful probe. And here is a plot that one can state it.
5 minutes left.
Okay, thanks a lot. Yeah. So here is a plot of collapse fraction for different models as a function of redshift. And You may ask, how do we compute this collapse fraction? I mean, collapse fraction is not an easy thing to, everything is collapsing, dark matter is collapsing, and that's what we really compute. And stars are forming, other kind of structures are forming. We cannot compute collapse fraction for most of these things observationally, but we can compute it for neutral hydrogen based on damn Lyman alpha survey. Now, it's a very, very interesting probe, which was used initially in early 1990s and late 1990s based on a handful of damn Lyman alpha clouds. In those days, like they were around 30 or 40 damn Lyman alpha clouds. So what you see is you have distant sources, quasars, thousands of them, and you look for a certain specific absorption feature in their spectra, which correspond to very large column density of H1. And because it's a random distribution of H1 in front of a random distribution of quasar, you can actually convert a column density into a volume density. Over a period of time, this observation improved. Now, DR9, that is basically SDSS, and this is based on 7,000 quasar, 7,000 damn Lyman alpha clouds. So this area of research has progressed dramatically from late 1990s, where there were a handful of damn Lyman alpha clouds, on 30 or 40, when I first started looking at this. And currently there are 7,000 to 8,000, and my number could be wrong. It increases every day. So we have a pretty good idea, and these error bars are very tiny, of the fraction of H1 that has collapsed as a function of redshift. And you can see it in these plots that it's indeed reasonably well constrained. And when you go to very high redshift, the data are not so good. But point is, this is the minimum amount of matter that would have collapsed. So there are other things that are collapsing, but at least this has collapsed. So every model that is acceptable should show a collapse fraction which is larger than this value, right? If something showed larger than this value, it is unconstrained. So all these models like CDM, I've plotted a whole range of models for MA. This is the mass of the ultra-right AXIONS. All of these models are actually unconstrained by these observations, because they simply say the collapse fraction is more than H1. Well, we expected that, didn't we? But there is one model that's actually ruled out. When you go from MA, and you can see because of the exponential dependence, the collapse fraction is extremely sensitive. You jump from 2.6 into 10 power minus 23 to just 1 of 10 power minus 23, less than a factor of 2, roughly a factor of 2, and the collapse fraction collapsed. Collapse fraction collapsed, yeah, way to put it. And this model is actually completely ruled out by the model, by the observation. So it's actually a powerful probe of all kinds of dark matter models. If you have a dark matter model, it is always a good thing to do this simple exercise to see if the collapse fraction.
Sorry, Shiv, you are breaking up.
Yes, sorry.
We lost the connection for a second. Yeah, go ahead.
You couldn't hear me? Hello, can you hear me, Rishi?
Yes, we can hear now.
Okay, sorry. Yeah. It says my internet connection is unstable. So I'm sorry.
We lost you for a few seconds.
Okay, fine. Okay, so now I'm back. Yeah. So thanks for telling me. So this is another thing that we can actually get from epoch of reionization. Now this is a plot based on a simulation. This is a redshift of 10, and it's a two-dimensional slice of what we expect from lambda CDM model against what we expect for another model. And these are all models of ULA for different values of the mass of the AXION, the ultralight AXION. And one thing that you cannot escape is that for lambda CDM, these features, so these are ionized features. The dark blue is ionized and things around it could be neutral. So you can see the size of ionized regions is much larger when there is AXION. And this comes from two reasons. One is, so there are fewer halos that form and ionize in the case of an ultralight AXION. So you may wonder, if there are fewer halos, there should have been less ionized regions. No, when there are fewer halos, they cluster more strongly. So the fewer the halos, they cluster more strongly. So one ionized region does not arise from, in this lambda CDM model, also they are clustered, they might arise from a few like sources. Here they will arise from a larger number of sources, so they're more clustered because they're fewer. And second, this is matched to the same ionized fraction. You still have to, and what you would see is that the ionized regions will be much larger. One may say, oh, well, maybe we can actually image them, and that would actually settle this issue for us. But imaging them is next to impossible. I mean, not now, but even in the coming years, it may be very, very difficult to do. but it might become possible in around 15 years. I mean, SK might get there finally. But one probe that we have currently is that we can actually compute the H1 power spectrum. So that limits information. So what we can do is we can take this feature and we can compute its power spectrum. And the power spectrum is enhanced simply because of the fact that the ionized region is larger. And you can see it is enhanced by a factor of 4 to 5 over what you would expect from the lambda CDM model. For all the cases, I've shown two classes of model, just focus on the right panel, which is the ULA. And you can see as the mass of ULA is decreased, the signal becomes more powerful. It becomes larger, and this is around a factor of 5 or 6. It'll be a nice probe. I am still not sure that one might be able to distinguish between models based on just this probe, but we are still waiting for early result in this area of research. So, I mean, in the next 4 to 5 years, we may have something. And we may first have a detection, and then we may be able to start modeling what the detailed outcome of the detection is. So this is my summary. The nature of dark matter is still unknown, in spite of the successful lambda CDM model. Many cosmological observables, and I focused on two in this talk. Like this is the collapse fraction of H1 and the epoch of reionization were the two things I discussed in this talk. And H1 signal from epoch of reionization. I mean, it's a very exciting possibility that in the coming years that it may actually reveal the nature of dark matter. And there are multiple experiments going on. I myself am involved in MWA, I mean, analyzing the data of at least one of those experiments, and many of us are involved in SKA. I mean, and that data may take another 10 years to come. CMB spectral distortion, I mean, didn't talk about it. That's another probe of the dark matter. I'll stop here. Thanks a lot.
Okay, thank you, Shiv. So we have, I think, time for maybe a couple of questions. So first question is by Raghavan Rangarajan. So maybe you can unmute yourself and.
Sure. Hi, Shiv.
Hi, Raghu. How are you?
Good. Long time. On slide 9, I think when you were talking about structure formation.
Yes, 9.
Oh no. Okay, maybe you said that for scalar field dark matter, there's a delay in
this one
from when structure formation starts. Yes.
That's right. Yeah.
So does that significantly affect the time one has to form structure?
Well, you have to tune your model. So the point is like, yes, of course it does, right? But one has to tune the model. So you can actually see that structures, so tuning the model, basically there's one parameter in the model, which is like the mass of the axion. You also have to fix the initial condition to get the density parameter right? The density parameter is like something which is not discussed here, but you have to fix the scalar field so the density parameter is right. So clustering is happening at large scales, which can be compared to other CMB and large scale data. But at small scales, yes, it could be curtailed, and it is, as you can see. So there is less time to form structures. Absolutely.
Right. Thanks.
Okay, Subinoy has a comment.
Hi, Shiv, Subinoy here.
Hi, Subinoy.
So actually in the talk, David Moss and Vivian both pointed out there is a recent paper by Lyman alpha by Hiranya Perry's group. This even put the most stringent constraint on ULA dark matter. It came down below 10 to the minus 22. So only 10% or 5% of fuzzy dark matter is allowed. So it will be very good to see that.
By the way, I have done analysis with Lyman alpha. I think that is a little too much actually, that limit. I mean, my sense is that the limit cannot go beyond that. That's based on Lyman alpha, right? The paper you're talking about?
Yeah, yes.
See, Lyman alpha cannot go beyond k equal to 4, roughly.
But it's a very recent paper. It's a very recent paper, just few weeks back. So maybe
a few weeks back. No, this is a paper like which around 1 year ago, I remember.
Oh, yeah.
Okay, which was like, okay, I'll take a look at it.
Yeah.
Because Lyman alpha, we have actually been doing work on this. Lyman alpha will constrain a little better than this, right? But not substantially better than that, okay? Because it's difficult to get information below k of few. I mean, and k of few will get you around 10 to the power minus 20. So maybe we are in agreement actually here.
Yeah.
Okay, Shantanu, you have a question? Shantanu?
Yeah, can you hear me? So, okay, so this is not directly related to the core content of your talk, but since you discuss observations, right? So anyways, in August, there was a paper by Andy Burkert who pointed out that most of these fuzzy dark matter and ultralight dark matter models, the halo surface density decreases as a function of the core radius, whereas observations show that the halo surface density is constant. So do you have any comments? I apologize if this paper was discussed in some other talk, but since your talk
I
was...
actually haven't looked at it, but it's absolutely true that the halo surface density will decrease. But again, this all comes within like the purview of what we'll call uncertainty in observation. Okay. So absolutely. So the point is, like, best way to probe these models would be to look at, for instance, so density of objects like as a function of redshift. But there are huge number of selection effects which actually come in while we try to interpret data there. So we actually looked at that. Actually, that was a part of the paper. I did not even discuss it. That when there is data all the way to redshift of 7 to look at halo densities. Okay.
Yeah, but at redshifts of 0, right? I think the halo observations show, at least for more than a decade, that the halo surface density is also almost constant. Although I think Antonio Del Popolo disputes this. We have been having email exchanges about this,
Okay.
and that's the point made by Andy Burkert in his paper. So that's why.
But why should the halo density remain constant?
No, that's an observational fact. If you fit it to, if you just fit it to, so observationally it is constant, but these ultralight dark matter models predict that it should decrease. So that's why it is ruled out. That was the argument in Andy's paper.
I don't think like they will have much to say at redshift of 0. I'd like to look at those papers. Actually.
Okay. I think I'll send the archive number. I send it to Subinoy.
Yeah. Sure. Yeah. Thanks.
Okay, so I think one last question by Trupati. I can maybe just read it. So what is the yellow structure on slide 13?
This one?
Slide 13.
Slide 13, it would be this one, right?
No, the picture. I think the map, the simulation map.
A simulation map, this one.
Okay.
Correct.
So there is some...
Correct. So these are, this would be the halo. Okay, this is the ionized region and most of it. So over density of the region. So the point is like, you can actually see what is plotted on this side is the brightness temperature in millikelvin. So where it is dense, actually, the brightness temperature would tend to be higher. So blue is empty. Blue is basically ionized, right? And we keep some information about the brightness temperature that you would actually expect in the H1. So that is where the yellow and the red, you can see it's on the right panel. That's what the information is.
Okay.
Yeah, it's difficult to actually see it. One has to see it larger.
Yeah. Okay, but anyway, so I think it is understandable now. So thank you, Shiv, for a very nice talk.